So let us kind of try to understand or gain more insight by doing an example. Discrete time signal representation. Let us take an example. I am going to draw the discrete time axis, n axis, the y axis, and take some analog signal. I am going to take a simple triangular waveform. This is an analog signal. Now the n axis, I am going to split it up into equal parts representing the sampling time. So this is xt. I have split up the n axis into equal parts. Each part is 1 t length. This is 1 t. This is another t. This is another t. Okay, this is 1 t, 2 t, 3 t, 4 t, 5 t, 6 t, 7 t, 8 t. Where t is the sampling period. You sample at this regular interval. It is a design parameter. You decide what should be the sampling time. We will come to that later, much later, how to decide on the sampling time. So you have the sampling time, and these are the points of intersections with respect to the sampling time. So this is one sample. This is another sample at 0.5 value. This is at 1, in 0.5, 0, minus 0.5, this is minus 1, minus 0.5 and 0. So this is how it has been sampled, and these are the values. X of t equal to 1t is this, x of t equal to 2t is 1, x of t equal to 3t is 0.5, and so on. Now let us represent in the n domain, the time domain, discrete time domain. So I will say this is xn. So I sample, hold it, then sample, hold it, sample, hold it, sample, hold, sample, hold, sample, hold, like that. It keeps going, right? That would be the discretized version of the symbol. So I will take this at 0. Value is 0 into delta n plus 0.5 into delta n minus 1 plus 1 delta n minus 2 plus 0.5 delta n minus 3, 0 delta n minus 4, right? Then minus 0.5 into delta n minus 5 minus 1 into delta n minus 6 minus 0.5 into delta n minus 7 plus 0 delta n minus 8. Okay. So this is what you would get by the discrete time impulse train representation. Now if you represent it as a Z transform signal, x of z. So if I take this as x of z, now it is 0, z to the power of minus 0. So this is at time 0. 0.5 z to the power of minus 1 at 1 sample time. At 2 sample time, value is 1 z to the power of minus 2 plus 3 sample time, value is 0.5 z to the power of minus 3 plus 0 at 4th sample time, minus z to the power of minus 4. Then at 5th sample time, minus 0.5 z to the power of minus 5, minus 1 z to the power of minus 6, minus 0.5 z to the power of minus 7, then plus 0, this is 0 at z to the power of minus 8. So the Z transform has converted it into a polynomial. This is the most important aspect. So this is the Z transformed representation of the discrete time representation of this signal, which is the representation of this analog signal xt. So what is the significance of Z to the power of minus 1? So we see that this is the signal sampled at various points, and the Z transform signal is something like this. Now let us say I multiply this entire equation by Z to the power of minus 1. What does it mean? So if I multiply, so xz into Z to the power of minus 1 would be 0 into Z to the power of minus 1, 0.5 into Z to the power of minus 2, plus 1 into Z to the power of minus 3, plus 0.5 Z to the power of minus 4, 0 into Z to the power of minus 5, so on, till you get 0 into Z to the power of minus 9. So let me write that down. xz into Z to the power of minus 1 will be just as I mentioned, so on up to 0 into Z to the power of minus 9. So it gets added up. Now let me replot this green, whatever is this green equation, I will replot it. So what does it mean? 0 Z to the power of minus 1 implies this sample occurs at one sample time. So at one sample time corresponding it is 0. So I will place that. Then at sample time 2t it is 0.5. Sample time 2t it is 0.5. At sample time 3t it is 1. So this is 3t, it is 1. Then sample time 4, okay, it is again 0.5. So place that there. Then 0 at sample time 5. Then minus 0.5 at sample time 6t. Then minus 1 at sample time 7. Then minus 0.5 at sample time 8. Then it will become 0 again at sample time 9t. So this, if I join up all the dots, you will see that I get again that same triangular waveform with one important change. It is delayed by, the entire wave shape is delayed by one sample time. And that is the significance of Z to the power of minus 1. Z to the power of minus 1 implies one sample time delay. Z to the power of minus k implies k sample time delays. So that is the important. Z to the power of minus 1 implies unit delay. So this is a functional significance. What is the physical significance? Any delay means there is a storage. There is a physical storage involved. So I have a value. So I want to keep it till the next sample time, means I put it into storage, and then once one sample time amount of time has elapsed, you then release it from storage, which means I need a memory location to store the value. So Z to the power of minus 1, one unit delay would mean one physical storage space or one memory unit. So it could be 1 byte of memory, or it could be 1 word of memory, or it could be 1 bit of memory, depending upon what is the memory unit one is thinking of in the discrete domain. So if I am using a 8-bit microcontroller or a 8-bit computer in the discrete domain, then one memory unit would mean 8 bits or 1 byte of memory. If I am using a 16-bit system or a 16-bit microcontroller, then one memory unit would be 1 word or 1 16-bit word. Or if I am using a 32-bit microcontroller, Z to the power of minus 1 would mean 1 32-bit word. So this is what Z to the power of minus 1 will signify. Very important to remember, because the entire discrete world will use this extensively. So Z to the power of minus 1 implies functionally a unit delay, and physically one memory unit. Now we shall discuss how to build filters in the discrete domain. Z to the power of minus 1, we discussed its significance. The functional significance is that it is a delay, unit time delay, one sample time delay. In terms of physical significance, it implies allocating one memory unit. Z to the power of minus 1 would mean one memory unit. If it is a 8-bit system, it is 1 byte of memory. If it is a 16-bit system, it is 16-bit word as the unit of memory, and so on. So let us use Z to the power of minus 1 for building filters. Z to the power of minus 1 is the basic building block of all systems in the discrete domain. Anything that you want to build in the discrete domain, you have to use the Z to the power of minus 1 block. That's it. If you have that, you can build anything. So let us see how we can do that one. So let me take an input stream. It could be a stream of discrete, UN is a discrete signal, and it is passed through as Z to the power of minus 1 block. What it means is it is passed through a unit delay block. So which means that if it is passed through that, you are taking the value at k, putting that in a memory location, and then you will take the value out here at the next sample time. Okay, so if it is kth interval now, so what I get value is u of k here, and what I would get here is the previous value of k is released now, which is uk minus 1 value is released now. So that's what this block will imply. The kth value at kt time interval, whatever the value of u is available here, and what is available here is one sample time before, u of k minus 1 t. So keep that in mind. So then let us say that I will put one more Z to the power of minus 1 block. I will cascade it in this fashion, and so on I will cascade. So imagine that I have several blocks, unit delay blocks in cascade, and the topology is like this. And now I am going to scale, I am going to drop off, I am going to pick off the values from each of this, and then I am going to scale. So I will scale this with A0, I will scale this with A1, right, and then scale this so on with A2, and so on. If there are m blocks, then this will be AM. So these are scalar values, scaling factors. These are scalar values and scaling factors in this fashion. What you should understand is, now if I take the present moment is u of kt, the value at kt is u of kt, then the value that is available here would be u of k minus 1t. The value that will be available here is u of k minus 2t. The value that will be available here is u of k minus 1t. Basically, because this is what you have is z to the power of minus 2 in you have two blocks in series. You have m blocks in series, z to the power of minus m. So after m delays, the value available there would be the present value of u delayed by m sample times. That's what it would mean. So now I will put a summer. This is a summer block, and I'm going to add all these outputs from the various delay block. So I will add the output coming from the undelayed scale value, then 1 time delayed scaled value. I will add that 2 times delay scaled value, m times delayed scale value. So all this are added up and I get the output, right? Yn. So this is one form of filter. This is the output Yn, right? And this is the input stream. Let me adjust the size of this page so that we can see a bit more of the blackboard. So let me now draw the x-axis, which is the discrete time axis n, and I draw the y-axis. So the y-axis is nothing but yn, which is the output discrete time signal. This signal yn. So let us do some plotting. I am going to divide the discrete time axis as 0, 1 sample time, 2 sample time, 3 sample time, 4 sample time, so on. And let us give a input, one impulse for the input. So this is one single impulse that I am giving for the input at time t equal to 0. What would happen? So at time t equal to 0, I am giving one single input impulse. Now that will flow through the scaling factor A0 and come to the output. All others are initialized to 0. So this is 0, this point is 0, and this point is 0. So this value is A0 because this is passed through the scaling value. Now after the elapsation of one sample time, what has happened? The previous value, what was at 0t, is now available here. At the present moment, after the elapsation of one sample time, this impulse, the value here is 0, the impulse was at 0. At 1t, the value here is 0, but it is 1 here, because the delayed value is here. That 1 now passes through this A1 scaling factor and goes on to the output as A1. Then after two sample times, you will see that the impulse would have shifted here. The value k minus 2 is 1 here, passes through A2, and it is available as output, and that is value A2. Yeah, I'm just putting some arbitrary value of scaling constants here. And then so on, after m sample times, you will have AM coming to the output, right? So after M sample times, you will have AM coming to the output. After that, all the nodes from the M plus 1th sample time, this would be 0, this would be 0, this node is 0, this node is 0, all the nodes are 0 and therefore output is 0. So after that, you will see that there is no output from the filter, from whatever this filter is. So if I give one input impulse, one single input impulse, after M sample times, the output becomes 0, where M here is after the number of unit delay blocks in cascade which are there in the system, the output becomes 0. So the output is there only up to M sample time, which is a finite number of sample times indicated by the finite number of unit delay blocks. So therefore, this is called a finite input impulse response filter, FIR filter, the finite impulse response filter. So now let us calculate what is the Z transformed value of this discrete Yn. So Yz equals, so what does it equal to? So you have this A0 value at 0t, so A0 z to the power of minus 0, right? So that is A0 z to the power of minus 0, which is 1, into u of z. So u of z into A0 is the one which goes on to give you the output. Plus, after one time sample, u of z into z to the power of minus 1 goes through A1 and to the output, right? So A1 u of z, z to the power of minus 1. Then third sample, A2. So you have u of z, z to the power of minus 2 into A2 will go to the output at the third sample instant, that is 0t, 1t, 2t. So let us write that down. So like that, you will see that after M sample times have elapsed, you will have AM uz z to the power of minus M. So this is the equation for this filter. Now if you take all the uz's, the common factor, and then they take it to the denominator on this side, yz by uz will give you the discrete transfer function. So let me write that down. Yz by uz, which will be A0 plus A1 z to the power of minus 1 plus A2 z to the power of minus 2, so on AM z to the power of minus M. So this whole thing is the transfer function of this filter. This is the discrete transfer function of this FIR filter, of the generic FIR filter. So this discrete system that we have described is called the finite impulse response filter, or the FIR filter. This is the generic filter. I will talk of specific cases later. A specific example of an FIR filter is a moving average filter, or you can also have another example, a difference filter, finding the difference of two values. You can also use the difference of two values on detecting the slope of a time signal. So the discretized time signal, if you want to find the slope of that, you could use a difference filter. So that is also a FIR filter. So now, if there is a finite impulse response filter, there must be an infinite impulse response filter too. So what is the topology of the infinite impulse response filter? So I start again with U of n. U of n is the input stream, discrete input signal that I am going to pass through a unit delay block. So I will do that just like the FIR filter. I will have m such unit delay blocks in cascade. And I will scale each of them, each of the points. I will scale and then I will add them up. And I will get an output y of n. The discrete signal yn is the output. Now this is the FIR filter. I'm going to add something to this FIR filter. So I'm going to take a signal from output yn and I'm going to delay that. So I'm going to take this signal yn, delay that through z to the power of -1 block, and then I can put a series of delays to the signal that I am going to feed back from the output, and then I will scale each of the nodes just as like I used A0, A1, A2, AM as the scalars for the feed forward delay blocks. For the feedback delay blocks also I will use the scale factors B1 to Bn. And then connect it up in this fashion, and together yn will be summation of all these signals put together. Now this is the feedback part, and this is the new addition which results in the infinite impulse response filter or the IIR filter. So let me draw again like before the n axis, which is the discrete time axis, and the y axis is nothing but the discrete time output yn. I am going to segregate or equally have click points on the n axis at 0t, 1t, 2t, 3t, mt, so on. And I will give one single impulse, unit impulse at the input here. So at 0 time t, A0 will go in and come to the output. So there is no confusion there. And now after elapsation of 1t, the impulse would have shifted here. So this impulse into A1 will come in here. But whatever the previous output was would have shifted here. The previous output was A0. So the previous output would have come here. So A0 value into B1 value will also come and add up here. So from the input A1, so this is the one which is coming in here, and B1 Y1, which is nothing but the delayed Y1 is nothing but A0, this value. And then afterwards that delayed value of Y would come here, and the 2 times delayed value, which is A0, will come in here. The unit impulse would have shifted here, passes through A2. So you will have unit impulse multiplied by A2 coming in here plus one delay coming in here, two delays of the output coming in here, adding up, and then you get the output. So like that, you see that even after m intervals, on the top side, the values are 0, because this would be 0, this would be 0, this would be 0, this would be 0 after all the impulses have been delayed, and finally that depletes. But output is there, and therefore the bottom values coming from the feedback will always exist and can gradually converge to 0, and it will be like an exponential decay. So therefore only at n tending to infinity you will see it 0, and therefore it is called infinite impulse response filter. Now, what is the equation for this? Let us write YZ equation. YZ equals. So first you take the forward part, UZ into A0, UZ into delay, Z to the power of minus 1, 1 delay into A1, UZ 2 delays, Z to the power of minus 2 into A2, right? M delays, UZ into AM, M delays. Then you take the feedback part, YZ delayed by 1 delay into B1, YZ, Z to the power of minus 1. Then so on you go along this feedback path. After n delays, Z to the power of minus n, YZ, Bn. Now this becomes your equation for this infinite impulse response filter. You can take out, what you can do is you can bring all the YZ terms to the left hand side, take out YZ as a common factor. On the right hand side, take out UZ as the common factor. YZ by UZ, you can get YZ by UZ. So I will put it here. I will lighten the background. YZ by UZ will be, all these blue terms will come on the numerator, A0 plus A1 Z to the power of minus 1, A2 Z to the power of minus 2 coming from here, so on AM Z to the power of minus M coming from here. Then the YZ terms which were here on the left side will come to the denominator, so 1 minus B1 Z to the power of minus 1 coming from here, so on minus Bn Z to the power of minus n. So this forms the transfer function of the infinite impulse response filter. Consider the transfer function of this IIR filter. So you see that there is a numerator polynomial in Z to the power of minus 1 and a denominator polynomial in Z to the power of minus 1. You can simplify this and bring it to pole 0 form. So if I take the denominator and convert it into the pole 0 form, you will see that the roots z minus p1, z minus p2, p represents pole, z minus p pole 1, z minus pole 2, and so on, z minus pole n. Because there is a z to the power of n coming in, you will see that there are n roots, and this implies n poles. All the poles P1, P2, Pn are not identical. They can be placed anywhere in the z-plane within a unit circle in the stable zone. So designing these poles appropriately will give you IIR filters of different characteristics. Likewise, the numerator also can be brought into the root form: z minus z1 0 1, z minus z2 0 2, so on, z minus zm. There are m zeros. So use the pole zero form whenever you are trying to visualize in the z plane, and whenever you want to do the design, you can place the poles and the zeros appropriately to get the characteristics that you want. If you look at the FIR filter, all the poles P1, P2, Pn, if it is a nth order, all the poles will be identical and placed at 0 in the case of the FIR. So that is one way of distinguishing between FIR and IIR filters. IIR filters, the poles are not necessarily at 0, but in the case of the FIR filter, all the poles will lie at z equal to 0. So if you look at the FIR filter transfer function, let me go back. So we have the transfer function of the FIR filter. So this is the FIR filter, right? And this part, so if I take out z to the power of minus m common out, so you will see that that will be equal to z to the power of minus 1, I am taking it out, a naught into z to the power of m plus a1 z to the power of m minus 1 plus a2 z to the power of m minus 2 plus so on am. So I will erase this, divide by z to the power of m. So this is the pole zero form that you will get for a generic FIR filter. So you will see that for FIR filters, there will be just z to the power of some m, where m will be the number of delay elements. This implies that all the poles are at z is equal to 0. So if there are m delay elements, if it's an mth order system, then all the m poles will lie at z is equal to 0 in the case of a FIR filter. Only the zeros lie at distinct places on the z plane. So if you are having m delay elements, you will have 0, 1, 0, 2 up to 0m, and you have the potential to design the positioning of the zeros. You have the ability to place the zeros appropriately to obtain FIR characteristics. However, all the poles has to be at z is equal to 0. So therefore, in an FIR filter, there is flexibility only in the design of zeros. Whereas in the IIR filter, there is flexibility in the design of the zeros and also the design of the poles. This is key important takeaway and also the distinction between the FIR and the IIR filters.